Hello, my name is Aribu Rahman and I'm the founder of FastMindJunction. I'm super excited and honored to be here with you today. At FastMindJunction, we are known for doing two things better than anyone else, clearing your doubts and making sure you never need those notes again. I'm committed to helping students like you letting go of their doubts and dependency on notes so that you can learn with clarity, with confidence, and with purpose. I believe you should spend more time exploring your future rather than fearing the exams because real learning starts when doubt ends. So we have this past paper here. It's WPH11 12th May 2023, and let's begin with this video. Okay, so we have this question here. It is asking us which of these options is vector quantity. Now, for those of us who have learned the list by heart, they know it's weight for sure. But let's say if you forgot the list and if you haven't learned the list, how would I know that which of these options is correct? So it's very simple. Vector quantities and scalar quantities have one thing similar, which is the value, right? It has some sort of value. But vector quantities have one thing that is different from scalar quantities, which is it has direction, okay? So let's check which of these options is linked with directions. So let's talk about efficiency. Now, for example, you have a machine, right? It's doing something, okay? And you provide him like 110 volts. You provide him this much of power, right? So you should know by now that 100% of this 100 watts is not going to be used. It's going to be wasted in some sort of sound, maybe some heat and power. Like it's being distributed, right? It's not been 100%. 100% of 100 volt is not being used, okay? So we use efficiency's formula to calculate how much of the power I provide is being used for this machine to operate well, okay? That's it. It doesn't have any relation with the direction at all. Even if you move the machine a little bit to the left or to the right, the efficiency won't change. The efficiency will remain the same. So let's talk about the next part, which is kinetic energy. What is kinetic energy? So you have this ball and it has some mass. Now this ball start moving at some speed. That is kinetic energy, simple as that, right? So it doesn't matter which direction you go, whether you go forward, backwards, left, right, or any diagonal directions, it doesn't matter, right? So kinetic energy has no link with direction. So let's go to the next option. It says power. Now what is power? Like for example, I have 100 joules, like I'm providing some machine 100 joules for 20 seconds, right? So power is how much you are providing, how much energy you are providing per second, right? Per second, for 1 second, how much energy I'm providing. That's it. It doesn't matter. It doesn't have any link to directions, okay? So let's talk about weight. Like other options are incorrect. So of course weight will be correct, but how would I know that weight is correct? That's the question. So for weight, weight changes depending on where you are. Like for example, Earth, Mars, Moon, right? But like they have one thing in common, right? Their gravity pulls you downwards, right? And that's the main thing. Like gravity is pulling you downwards. So this pulling you downwards has a direction, right? So we can say that weight has a link with direction. So if you even if you calculate weight is mg, right? Your mass and the gravity, right? The gravity value. So from this value you get how much you are being like pulled down. That's it. That's how I know that option D is correct. Okay, so we have this question here. It has given us force, displacement, angle, and it is asking us to find the expression for work done. So it's a very simple question. So whenever you get this question, the first thing you draw is your vector diagram, always, okay? Before even you start. So it's very easy to draw a vector diagram. So this is your point. I'm gonna draw the resultant line. This is your resultant, right? Okay. So it's going diagonally, right? And this is 225 newtons. So how will I draw the vector diagram? In a very simple manner, right? So you have to reach to this final direction, the one I have drawn the red dot here, by only using left, right, up and down, okay? So first I will go to the right side and then I will go to, downwards. So this is my angle, which is 40 degree. Sorry, I haven't connected it. Let me connect it properly. Okay. So this, now this is your 40-degree angle, and always this becomes 90-degree angle, right? Because it always forms a right angle triangle. So opposite to this angle is sine theta, and the one which is not your resultant line, in this case, this is my resultant line, right? This is 225. This was my resultant line. So the line which is not your resultant line and not your sine theta will always be your cos theta. Okay, simple as that. Now we have to form an expression. Okay, now if you can see that my force is happening diagonally, right? That's why I drew the vector diagram to actually get my values for my right side, how much force is on my right side, and as you can see the direction is going down, so how much force is below me. Okay, so work done formula is work done is equals to F into, which is force, into displacement. So you have displacement which is 450 meters, right? Now for force, right, how will I get force? So check whether they have provided you with the direction of travel or not, right? In this case, we have been provided. Sometimes you have to figure it out, sometimes you make by yourself, but in this case they have given us the direction of travel, and from that we have to create the expression. Okay, so it's very simple. Our direction of travel is towards the right side, and you can see that cos theta is going towards the right side. Okay, so we will use cos theta. Your theta is the angle, which is 40 degree, and then you will add a value which is 225, and you times it with cos theta always. Okay, so it's 225, right, times cos 40 times 450 meters, right? So this is your expression here. Now let's check the options. I can see option number B, so your option number B is your final answer. Okay, so we have this another question here. It is asking us to find the length and diameter for which it will produce the greatest extension for this copper wire. So it's very simple. You will write the Young modulus formula. Young modulus is equals to Fx by A delta x. Okay. Now if you expand it more, it will be Fx by pi r square delta x. Area is pi r square. Now if you want to write it for diameters, it will be Fx by pi, and then it will be 2d square delta x, right? Because as you know that diameter is equals to r by 2, so if you put 2 there, so it's r is equals to 2d. So now what values you're not interested in? You're not interested in Young modulus, force, and this pi and this 2 as well. Even if you just like write it as 4d square, you're not interested in this 4, right? You're only interested in extension, this thing right here. You're interested in original length, and you're interested in diameter only. Okay, so let's remove them. We are not changing their value, so we don't need them at all. Okay, so now you're left with x by d square delta x. Now keep delta x up here, so it will be delta x is equals to x by d square, right? So this is the case. If you want greatest extension, you need to have your nominator as a greater value, which is your original as a greater value, right? Your length of the wire, and your diameter should be less, or it should be not be changing at all. These are the two conditions while your original length is greater. Okay, so from option A, from start, I can see that this is not producing me like a greatest extension because these two values are the same, so there's no change at all, right? So you don't need A. And same thing goes for D, like making them both same is just not the right, right common sense, right? You need only the length of wire to be increasing, right? Even in option B, you're increasing the diameter. Increasing the diameter will lessen the extension value, right? So you don't need B. Now you're left with C. You have greater length of wire, and you have like it's not changing, or it's like it's not changing like we made like the statement before. If it's not changing or if it's less, then it will give us a greatest extension. So your option C is your best suitable answer. Okay, so we have this another question here. It has given us force extension graph, and it is asking us to find work done in joules, and they have extended this much of the spring. So in other words, work done is also energy, right? Because you have the same unit, joules. Now it's very simple. There's no like logic behind it. It's just you have the values. Now check which values do you have. You have force, you have the extension. Also, they have given the extension value, right? So you have force and extension, right? So what formula in the formula sheet I can use that will give me the value of energy, right? Which is in other words work done. So I can see that one of the formula is elastic strain energy formula, right? So it's E is equals to 1 by 2 F into delta X, right? So you have 1 by 2 force you need to get, right? As you can see that they have given the extension, so it's 0.3, tally it up and left, so you have 2.5 newtons, right? So just write 2.5 and delta X is like 0.3, right? So now let's check the options, right? Because this is our expression. Option B matches, right? Remember 1 by 2 is like 0.5. So yeah, your final answer is B. Okay, so we have this another question here. It is asking about Newton's third law. What is Newton's third law? Newton's third law says that every action has equal and opposite reaction, okay? So what does this mean? So we have one ball here, which is ball B, and it is stationary, it's not moving, right? So you have ball A coming towards left side and going to hit ball B, right? So once they collide, right, what actually happens behind the scene? When ball A collides with ball B, it will provide a force towards the right side, to the ball B, okay? Force, this is, let's say this is force A. Force A is came from basically the ball A colliding with ball B and giving ball B a force towards the left side. But at the same time, ball B will also provide the same amount of force and same type of force to ball A as well towards the right side. This is the, sorry, left side. Force A is on the left side and force B on the right side, okay? This is the force provided to from ball B to ball A, okay? And ball A provides the force A, like from ball A to ball B, okay? I hope you get it. So this is the things that are happening, right? It's in the different objects, right? Different objects, as you can see from the image as well. Like the forces act on the different objects, and it has the same value, same amount of force. It happens at the same time. There's no type of delay, and it's basically the same type of force, right? Same type of force. The force that ball A gave to ball B will give it back as return, okay? So let's check the options as well. So you have option A, it says same objects. No, force doesn't act on the same objects. As you can see, force B, ball B and ball A have, in different objects, they're having the same kind of forces, right? So option A is incorrect. They have the same value. Same value means same amount of forces acting on both objects. Yes. It happens at the same time. Yes. And basically it has the same type of force. Yes. Okay. So this option A is not correct. So option A is your answer. Okay, so we have this question here. It is asking us which of the options will give us gradient equivalent to gravity. Now it's very simple. We have to check each formulas and make A as subject, which is because A is equals to gravity. So we will make A as subject, and we have to check that if y-axis has one of these values and x-axis has one of these values, right? So from the option, I can see it has t square and t as well, right? So only one equation of motions has t square, which is s is equals to ut plus 1 by 2 at square, right? So if this formula doesn't have like anything from these options, then we will move on to next formula. So you know that u is 0 meter per second, so u will be eliminated. S is equals to 1 by 2 at square. Now we will make a as subject, so 2s, 2 goes up there, and t square is basically divided, so you're left with a. If you write it properly, it will be a is equals to 2s by t square. Now you know the gradients formula, which is delta y over delta x, right? So delta y is 2s and delta x is t square, right? So let's check the options if we have one right here. Option A, we don't have it. It has single s. Option B, we do have it, right? Yeah, option B is 2s and t square. And option C, s2t, nope. 2st, nope. So option B is your final answer. Okay, so we have this next question here. Let's check what values do we have in order to find the acceleration of the car. So we have u is equals to 3 meter per second, and then you have v is equals to 5 meter per second. You have s, which is 15, and you need to find a, right? So simple formula of equation of motion, which is v square is equals to u square plus 2as, right? And you have 5 square is equals to u is 3 square, and then you need to find a, and you have s, which is 15, right? If you make a as subject now, so it will be 5 square minus 3 square, and you divide 2 times 15, so 2 times 15 is equals to a. If you write it properly, it will be a is equals to 5 square minus 3 square by 2 times 15, okay? So let's check the options. Option A is incorrect, option B is incorrect, option C is also incorrect, and option D is correct. So option D is your final answer. Simple as that. Okay, so we have this question right here. It says we need to find the final speed for the object, right? So we have S, we have the angle, and that's it. It says from rest and frictionless slope. So we have S is equals to 20 meters. We have U, which is 0 meter per second. And we don't have time, we don't have acceleration, and we need to find speed. Okay, so let's see what we can do. First, let's identify what is actually happening here. The object is going down the slope, right? But how is it going down, right? Like something must be helping this box to go down. There's no frictional force. None of the force is provided by us. Then how it's going down? So it's very simple. Weight is actually helping it to go down, right? Weight is providing the acceleration. So you can see this weight. Now let's draw its components, right? To understand furthermore, like which of the component, either is the sine component or the cos component. Let's first figure that out, okay? So in order to draw the component, imagine this line to be a straight line, okay? Then you will be able to draw the components. So in order to reach, this is your resultant, right? The W is your resultant line, okay? So you need to reach here. You can only use up, down, left, right. So first I will go down, okay? And then I will go to the left side, okay? Let me try it a bit more correctly. This and this, okay? So this is your 90-degree angle, and this is your 23 degree. Opposite to this angle is always sine theta. And yeah, you will go down and then you will go left, okay? And this is your resultant line. The one which is not your resultant line or sine theta is cos theta, okay? So this is your cos theta. Now, what we need to do is we need to figure out which of the component is helping. Sine theta is helping because it is helping it to go to the left side or down the slope, okay? So W sine theta is helping it for the box of acceleration. It's helping the box's acceleration, okay? Now, if you just calculate this, you know that your unit is still newtons, right? How can we use this as our acceleration? We can use the formula of F is equals to ma. Net force is equals to the mass times the acceleration, right? So your net force, or basically the box that has the acceleration, is W is equals to sine W sine theta is equals to ma. And if you expand W, it is mg sine theta is equals to ma. Now cancels out. Now you're left with a is equals to g sine theta. Okay. So we have acceleration, we have initial velocity, and we have s. So we can use the formula v square is equals to u square, equation of motions, v square u square plus 2as. So you have to find v. So we can make this square come here. It's square root. Now you know that your u is basically 0. So we can just remove that, and you're left with 2. A is g, which is 9.81 times sine, and theta is 23 degree. Sorry, 23 degree. And then you have s, which is 20. Okay, that's it. So this is your expression here for final velocity. So you have t2. Option A says 2 times 9.81 times 20 times cos. Everything with cos is wrong. And then you're left with C and D. So let's check C and D. So you have one of the difference is 2 and 0.5. 0.5 is wrong. So your final answer is C. Simple as that. Okay, so we have this question right here. It is asking us which of the row is correct when the temperature of liquid increases. And we can use the formula of drag force, which is F is equal to 6 pi R viscosity V, right? So we are working with viscosity, we are working with viscous drag, which is drag force, and we are working with terminal velocity, right? You can see from here, when the temperature of the liquid increases, there is a greater terminal velocity, right? So when we are working with this, we are working with viscosity, and when we're working with terminal velocity. So this is constant, we don't need this, so you can remove this, right? So you're left with F is equals to viscosity and V. So let's make terminal velocity as subject. So terminal velocity is equals to F by viscosity, right? So we have a greater terminal velocity according to the statement. Let me make it red color, right? And it can only happen if your F value is greater and your denominator is less. And then if the second option is that if your F is greater, but your denominator is not changing. And the third option is that this is not changing, but your denominator is decreasing again. Okay, so you have these three: greater, less, greater, stable, stable, less. Okay, in these three cases you will get the terminal velocity to be a greater value. So let's check option number A. Option number A is this constant, so the next should be decreasing. No, it's increasing, so this is incorrect. You have constant, decreasing, this is correct. You have decreasing, okay, and this is increasing, this is incorrect. You will get your terminal velocity as a less value. This is decreasing and this is decreasing. This doesn't result in having a greater terminal velocity. It will also, your terminal velocity will also decrease. So your only option which is correct, which is option number B. So your final answer is B. Okay, so we have this question right here. We have two identical springs and a force being applied 45 newtons downwards, and this is the extension. And you need to find the stiffness for each spring in Newton per millimeter. Okay, so first thing is that the springs are in series, right? If you want to find the stiffness for each spring, you can use this formula, which is 1 by K is equals to 1 by K plus 1 by K, right? So this is your stiffness right here, and just write this fraction properly. So it's 2 by K, and if you remove the fraction from 1 by K stiffness, it will be K stiffness is equals to K by 2. This actually gives you the stiffness for each spring, okay, for a single spring. So you can use the Hooke's law formula, which is F is equals to K delta X, okay. So you have force, which is 45 Newton, and you have stiffness, which is K by 2, and then you have extension, which is 15 millimeter, okay. So now if you make it as subject, it will be 45 divided by 15 by 2, right? If you write it in proper fractional form, it will be 45 times 2 divided by 15. So this is our expression. Let's check from the options. So 45 times 2 is this one right here by 15. So this is your final answer. Option number D is your final answer. Okay, so we have this question right here. It says a rock falls from rest through a small distance s to the surface of Mars. The rock hits the Mars with velocity vm. And then you have another rock falls from rest through a distance s, same as Mars, to the surface Earth and hits Earth with velocity ve. Now you need to calculate this in this ratio. You have acceleration due to gravity on Mars 0.38 g, and the ratio should be Vm by Ve, velocity of Mars over velocity of Earth. Now let's do this question strategy with a strategy, right? So it's much easier to solve this question. So your first step is to identify what values do you have. So you have Mars. For Mars, you have u is equals to 0 meter per second, and then you have s, which is s, and then you have final velocity as vm, and you have acceleration, which is 0.38 g. Now for Earth, you have the same thing, almost the same thing, which is u is equal to 0 meter per second as s. You have final velocity as ve, and then you have a as g, gravity. Now the second step is to identify which formula can we use, right, to actually get this ratio right here. And we have to select it from the equation of motion. So we have u, we have s, we have v, and we have a. So one of the equation of motion's formula we can use is v square is equals to u square plus 2as. Now let's input the values for Mars and Earth. So for Mars it is vm square. Your u is 0, so you can remove it. You are left with 2a and s. So a 2, and then you have a is 0.38 g, and then you have s as s. For Earth you have ve square, and you have 2 times g times s. Okay, now write this in this fractional form. So you have vm by ve square is equals to 2 times 0.38 g, and s by 2 times g times s. So now you can eliminate this s, right? Let's eliminate some stuff because they're actually the same stuff, right, on Mars and on Earth. So you have same s, you can remove s, you can remove the g, you can even remove the 2. Now what are you left with? You are left with vm by ve square 0 equals to 0.38. Now we still haven't reached to vm by ve. They still have square. So how we can remove the square? We can write this exact same thing like this, vm by ve, but write it as whole square, right? They both are the same thing. If you want to do the comparison, you can just add vm value, some value, and for ve add some value and calculate it. If they are both the same in both of the writing way, whatever, then you know that it is correct and I have written the correct form. So it is equal to 0.38, and now you can shift the square to the other side. So it will be vm by ve square root of 0.38. Now if you calculate this value and round it off to two significant figures, you will have 0.62. 0.62 is your answer. Now to understand significant values, you just see from the values that you have been given already. So from the value of Mars, I can see that they have written their Mars value in two significant figures. So it's a best approach to write your answer as well in two significant figures. Okay, so this is your final answer. Okay, so we have this question right here. It says a man dives from a platform into a swimming pool. The platform is like 12 meters above the water surface as shown. So we have this man here and he's about to dive into this water, right? So the graph shows that the vertical displacement of the man from the water surface after leaving the platform. So we have this graph here as well. And the first part says that state how the graph shows that the man's initial vertical velocity is zero. Man's initial vertical velocity is zero. I'm gonna very simply explain you why it is zero, okay? I'm gonna explain you through the concept of tangent, right? If you solve anything with tangent, it's like really easy and it's very easy to understand what is a tangent, right? So this is your initial point right here. Let me make it red. Okay, now your tangent will be something like this, right? Sorry, yeah, you can get the idea, right? So if your tangent is a horizontal line, right? Horizontal line, right? It means that there is no velocity at all. Simple as that. If your tangent has a horizontal line, it means no velocity. If it's like somewhere at this point where you draw this something like this kind of line, right? Something this kind, that means that it has some sort of velocity, some sort of change in velocity, right? So just mention here that your tangent, sorry, let me make it black. So your tangent is horizontal, right? Which means that your v is equals to 0 at point t is equals to 0, right? Like this point, t is 0 here. So yeah, okay, so we have this next part here. It says determine the vertical velocity of the man as he enters the water. Very simple, okay? I'm gonna explain you through a strategy known as the tangent strategy, right? So they said as he enters the water, right? So at this particular point, let me use a different color. So at this particular point, he enters the water, right? As he enters the water. So in order to draw a tangent line, there's like very easy, right? So when you draw it, make sure that, like, for example, let me draw a sample line. I will show you my working as well, but let me draw a sample line, okay? So let's say this is my sample line, not that beautiful, but it's a sample line, okay? Now you just drawn a tangent line, which is a bit tilted. Don't make it super vertical. It means that the object is moving, but the time period is not changing. So this vertical line, according to this graph, is completely incorrect. Okay, so don't use it at all. Best advice there. Now you use a bit of tilted line, okay, and then you have to check whether this part, like just say this much part or this much part, whatever the part you select, this much part is equal to this much part. And for now you can see that they are not actually not equal, right? So you have to just make sure that both of these sides have or like are actually a little bit close to being equal, right? Not perfectly equal, just being close to being equal. Okay, so I have drawn a sample line, okay, just to save us some time, okay, so that we don't spend most of our time on this video using trial and error. So let me remove this and reveal it. So this is the line I drawn, okay, I have drawn. So as you can see that this much of this area is almost equal to this much of this area, right? It's not perfectly equal. I know you might be wondering, oh, it's not perfectly equal. Like this is wrong. We will consider this wrong. No, you don't have to be perfect. You just have to be almost equal to this, okay? So this is almost equal, right? Not perfectly equal, almost equal, right? Let me draw this again. So Now your second step, this was your first step, tangent line, okay? Second step is to select 2 points, right? Points. You need to select points. And those points should be further away from this point, right? So as you can see, I have did it by myself. You can also select it from, like, you can go closer a bit, but I suggest going further, right? As much as you can go further, okay? So I've selected this point right here and this point right here. Okay, so these are my points. And your third step is to just calculate the gradient, because the gradient is equal to the velocity, right? And you need the velocity, right? So velocity equals to gradient, which is equals to change in y over change in x. And your change in y is, let's take down one as, you can start from, you can choose any y1 and y2. You can do anything you want, right? It's up to you. So let's say that negative 6.5 minus 12 by 0.6 minus 0.6 minus, sorry, not 0.6, my bad. 2 minus 0.6, 2 minus 0.6, right? So now, if you calculate this value, you will get your answer as, like the one I got my answer as 13.214 blah blah blah. You can round it off and write minus 13, sorry, minus 13.2 meter per second. Okay, so this is your answer. Negative is optional, you don't have to write your negative, but I would suggest write it, because at the next part you will actually use this answer, right? So let's go to the next part. Okay, so the next part says that before entering the water, the man has a constant vertical acceleration. Constant vertical and acceleration. After entering the water, the man has constant vertical deceleration. Draw the velocity time graph for the man on the axis below. So let's check, when does he enter the water? What time? He enters at 1.5 seconds, right? So 1.5 seconds comes here, and as you remember our previous value, my previous value, which was 13.214, you will use your previous answer here, right? And I rounded off to negative 13.2 meter per second. You will, whatever your answer from the previous value is, just write it here, okay? Now you will navigate this negative value here, so it's negative 13.2, so it comes somewhere around here, let's say, yeah. And you will use your scale and connect this point to this point right here, okay? So should be something like this. Sorry, right. Whoop, and whoop. Okay, so now what you need to do is check the ending time. Okay, so ending time I can see is here, right? If I tally it up, and it's 2.1 seconds, right? So 2.1 seconds is here. So now complete your stuff. This is your constant vertical deceleration. Okay, Whoop. So you have constant vertical acceleration and constant vertical deceleration. Constant means in graphical form a straight line. Okay, straight line. So yeah, this is your answer. Okay, so we have this question, next question here. A high-speed train accelerates from rest along a straight horizontal track. The final speed of the train is 76 meters per second. Show that the useful work done to accelerate the train is about 2 gigajoules. Now the mass of the train is 7.2 times 10 raised to power 5 kg. So you have to solve this question with a strategy. What is that strategy? The first step is to write the values you have. You have final velocity, which is 76 meter per second, and you have mass, right, which is 7.2 times 10 raised to power 5 kg. Sorry, kg. Now the second step, think of the formula which will help you get work done. Okay, formula. So work done, what is work done? Work done is like another form energy. Okay, and what is the energy formula? Because why I say an energy, because if you notice the units, it's like work done has a unit joules and energy also has a unit joules. Okay, so they're basically they're basically the same thing. Now to get energy from the formula sheet, I can see that I can use the formula of kinetic energy, right? Kinetic energy is, wait, E is equals to K 1 by 2 mv square. Okay, and this will also give me answer in joules, kinetic energy. Okay, so the next part, so the next step is to just input the values. So if you input the values, it is Ek is equals to 1 by 2, m is 7.2 times 10 raised to power 5, and then you have speed, which is 76. And if you write your answer and in rounded off form, it will be somewhat around 2.1 times 10 raised to power 9, right? It was something like 2.08 times 10 raised to power 9. Yeah, and you should know that giga is basically 10 raised to power 9. Okay, giga is 10 raised to power 9. So if you replace this 10 raised to power 9 with the word g, it will be something like Ek is equals to 2.1 g joules. Make sure to write your units as well. Don't forget your units. You will lose marks if you forget your units. So I have hence proved that your useful work done is to accelerate the train is about 2 gigajoules. Okay, so we have this next part here. It says the train accelerates for 180 seconds. The train has an input power of 16 megawatt. While accelerating, determine the work done against air resistance as the train accelerates. So it's very simple question. We need to just follow the strategy. And what is the strategy? First, identify what values we have been given. So we have time, which is 180 seconds, and we have power, input power, which is 16 mega. Mega is 10 raised to power 6. 10 raised to power 6 watt. Okay. Now, second step is to identify what they are asking us, right? Identify what they are asking us. They are asking us to find the work done against air resistance as the train is accelerating. How will I find that? Okay, so a train, in order to move, like at start, basically a train is given some power or even has some work done while it is accelerating, right? So if you can see from the statement, it was given this much of power, right? It was given 16 megawatt, right? While it's accelerating. So from this power, input power, this total power, some of that will be used against air resistance and some of them will be useful, which will be helping us to make that train go forward. Okay, two things. So you first, from this statement, we will get our total work done, right? And from that work done, some of them will be given to air resistance, AR, and some of them will be useful to us. So we have to identify this WT, and then you have WU, which is useful work done from the previous part, 2.1 times 10 to the power 9, and you can calculate WAR, right? So WAR is equals to WT minus WU. Now, which formula can we use to get the work done? So we can use power is equals to work done by T. So power is 16 times 10 to the power 6. Work done and time is 180 seconds. Now if you calculate this, and you will get your work done as 2.9 times 10 raised to power 9, right? This is your total work done. And now we will use it here, which is work done against air resistance is equals to total work done, which is 2.9 times 10 raised to power 9 minus the useful work done, which is 2.1 times 10 raised to power 9. If you subtract it, you will get your value as 0.8 times 10 raised to power 8 joules, right? Sorry, not 0 point, my bad. It's 8.0 times 10 raised to power 8 joules. Sorry. So this much of work done is done against the air resistance. Yeah. So just write it here. And I hope that you understood this whole concept. Okay. Do it strategy by, strategic way, step by step, and you will get your answer very much faster. Okay. Okay. So we have this next question right here. It says a sportsman hits a ball with a bat. The ball leaves the bat at a speed of 37 meters per second at an angle of 53 degrees to the horizontal as shown. Calculate the horizontal distance traveled by the ball before returning to the height it was hit from. So it's a very simple question. Let's do it step by step. For these kind of question, the first step is to draw the vector diagram. Okay. How will I draw it? So this is your resultant as shown from the diagram, 37 meter per second. This is your resultant line. Now it's very easy. Okay, I'm going to tell you a very easy way. Okay, so you have to reach to this point. Now you can use only up, down, left and right. Okay, so how will I reach here? From this point I will go first right and then I will go up. Okay, simple as that. Right and up. So this way it will form a 90 degree angle, which means it is a right angle triangle. Okay, and this angle is from here it is 53 degree. Okay, now opposite to this angle is sine theta. And if you might get confused, like how will I know what is cos theta? The line which is not your resultant line or sine theta is always your cos theta. Okay, for example in this. Now you have done your first step. Now let's identify your second step, basically identifying the values that you have been given. So let's do it for the vertical component. Okay, vertical component, right? So for vertical component, what do you have? You have u, which is 37 sine theta, sine angle is 53, and then you have a, gravity, which is 9.81. Now remember a very important thing. Okay, you can only choose your direction of motion, basically where your ball is going. Like if you want to consider that, if your ball is going up, if you want to consider the positive value up, then all of your values that are related to that direction is positive. Like for example, if you select that you have a positive motion of direction upwards, then whatever the values that are facing downwards will be negative, right? For example, in this case it will be gravity. You will have a positive initial velocity, but you will have a negative g, right? So you will have a negative 9.81. Now what else value do we have? We don't have s, and we don't have t as well, and we don't have even v. No, we do have v. Oh wait, yes, we do have v. And you might be wondering, where, dude? I did not see that. So I will tell you a very good strategy. It is that just make the graph into half. Okay, for only vertical component it's valid. Okay, so make it at half. Okay, now the time from here to here will be equal to the time from here to here, right? So v here is 0, right? It's like reaching to a stationary point at the top, right? So if you calculate the time from here, okay, and you should know by now that the time has no restrictions to the components, right? It doesn't matter whether it's a vertical component or a horizontal component, the time will be same. Okay, So if we calculate the time from here to here till v is equal to 0, then it's the same from v is equal to 0 to the end point till here before it returns to the height from where it was hit from. Okay, and you can just multiply it by 2 the time you get from here. Okay, so let's do that quickly. We can use the formula. We have u, we have u, and we have a, we have v as well, and we have to find t. So we can use the equation of motions formula, one of which is it is v is equal to u plus at. So you have u as 0, you have you have v as 0, you have u as 37 sine 53, and you have a as gravity, negative gravity, which is negative 9.81. Okay, let's not write it g, and you need to find t. So let's calculate your value of t, right? If you reassign it, write it properly, this thing will go here. It's negative 37 sine 53 by negative 9.81, and it will be equal to 3.012 seconds, right? Something like that. And you just multiply it by 2 so that you can get the whole journey's time. So it will become, let's see what it will become, 6.02 seconds, right? I have rounded off, but don't use rounded off value for future calculations, okay? Like further calculations. So you have 6.02 seconds. Now, interesting part. Now let's do the vertical side because we have to calculate the vertical distance, okay? So for vertical distance, right? Sorry, not the vertical, horizontal distance. My bad. Horizontal distance, to do it for horizontal component, right? Horizontal component, and you have u, which is 37 cos 53, right? Cos 53, cos here. You don't have any acceleration. As far as I can see, there is no acceleration given to you, and they basically, even without it, your acceleration is actually 0. Why? Because it's a constant journey. You can even see it from here. It's a constant journey. Otherwise, we wouldn't have been able to calculate our time if it wasn't a constant journey, because if it's like this is bigger, this side is bigger and this side is smaller, then you can't actually calculate your time, because for the total journey, the time will be different. Okay, so your a is 0 meter per second square, and you have you need to find s, right? And you have t. Okay, so from this, we can use the formula S is equal to one of the equations motions formula. S is equal to ut plus 1 by 2 at square. So your S, you need to find your u is 37 cos 57, right? And you have the t value, which is 6.02, and you know a is 0, so this whole thing will be finished, right? That's why if you have seen that normally people just say that S is equals to UT for horizontal components, always use this. That's how we use this, because we always consider that the total, like the total journey had a constant velocity, right? The velocity wasn't changing. So that's why. So that's why we always use S is equals to UT, just acceleration, making acceleration as 0. So now if you calculate this value, you should get 134.1 meters. Okay, rounded off, and it is something like 134 meters. Okay, not even three significant figures. Like normally it's recommended to use 2. Why? Because as you can see, 2, I can only see 2 stuff, right? So it's better to just convert it into 2 significant figures. So it should be 0. Okay, 130 meters. So 130 meters. So this is your final answer. I know it's a long video, but I'm just doing it with you so that you don't think I have just written the answer somewhere and I'm just like explaining you how to do it. I just did this whole thing with you. Okay, And I'm explaining you step by step on how to do this question, right? It's very simple. You just have to do step by step in order to understand everything, okay? So this is your final answer. Okay, so we have this next question right here. It says that the diagram shows a machine used to launch tennis balls in a horizontal direction. The machine is on frictionless wheels. Before a tennis ball is launched, the machine is stationary. Explain in terms of momentum why the machine starts to move as the ball is launched. Okay, it's very simple. Let's first understand what is meant by the frictionless wheel. The machine is on frictionless wheel, right? It means that there is no external forces, right? If there is no external forces, then it means that the total momentum is conserved. What is the momentum's rule? There should be no external forces, right? So the total momentum before is equal to the total momentum after, right? Because there is no external forces. Just mention that. The first thing you will mention here. You can either say the total momentum is conserved because of no external forces, or you can just write the whole thing, which is total momentum before is equal to the total momentum after, because there is no external force, right? Now let's go to the next point. It says that before a tennis ball is launched, the machine is stationary. Okay, so if the machine is stationary, then the total momentum before is zero, right? There's nothing happening, so it's zero. So it means that if total momentum before is equal to total momentum after, that means before is zero, then after will be also zero. That means that the whole process of momentum, that the whole process that is actually happening is zero. So we will say that total momentum is zero, right? So now the thing they ask us, like, why the machine starts moving then? If the total momentum is zero, it is because that the ball momentum is not zero after the machine, launches it. Like it has momentum, so machine has to make it equal, right? By going into the opposite direction to the ball's direction, and when you just basically add them up, the whatever the direction of motion you take, maybe right side as positive or left side as positive, you will add them up. One will be a negative value, one will be a positive value, right? And when you add them up, they will equal to zero. So you just have to explain that, right? Final momentum of the machine is not zero because the final momentum of the ball is not zero. Also add this additional point that they're going in the opposite direction, and they are going in the opposite direction. Simple as that. Explain everything so that you don't, miss any valuable marks. Okay. So it's very simple. Understand the statement and just reply the statement. Like you can see, I have like used nothing outside this question. I have used the question statement and converted it into my answer. Simple as that. So this is your final answer. Okay, so the next part says that calculate the velocity of the machine just after the ball is launched. Okay, velocity is given, mass of the both thing is given, right? So first step, identify what values is given. So we have velocity of the ball, right? And we have mass of the ball. We need to find, and we have also the mass of the machine, right? Machine. And we need to find the velocity of the machine, okay? Simple. we can use the conservation of momentum, which is m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. And from the previous part, if you remember, this whole thing is actually zero because the machine was stationary and the ball wasn't launched before, right? So this whole thing is zero. So you can say 0 is equals to m1. Let's say your m1 is ball and m2 is machine. Okay, so you have 0.056, right, times the velocity of the ball, which is 4.5 v1, plus m2 is the machine mass, which is 2.9, and you have velocity, which is you need to find, right? And I would like to mention a second point as well. If you remember that this is your machine, let's say this is your machine. I'm not good at drawing, so let's say this is your machine with these wheels, right? And you draw, this is your ball, right? Your ball is going right, but your machine will go to the opposite side, right? So that it can be your total momentum, it matches your total momentum before. Okay, so it's up to you whatever the direction of motion you want to take as positive. So I will take this positive value towards the right side, so my machine moving to the left side will be negative, right? So I can just add this negative sign right here. Okay, just add it here, or remove the plus sign and add negative here. It's up to you. So it will be 0.056 times 4.5, negative sign, you shift it on the left side, and now you will divide this 2.9, negative 2.9 is equals to Vm, and your Vm, which is the velocity, it will be equal to 0.0869. Okay, if you round it off, you will get 0.087 meter per second. So 0.087 meter per second is your final answer. Yeah. Okay, so we have this next question right here. It says a small spherical air bubble moves upwards in a glass of water, and the drag force on the bubble can be calculated using Stokes' law. State the condition needed for Stokes' law to apply to the bubble. So let's write the condition. The first condition is that it should be small. The second condition, it should be spherical. The third condition, it should be laminar flow, not turbulent, laminar flow, or you can say not turbulent, not turbulent. And the fourth one is relatively low velocity. Okay, these are the four conditions. Main are like the mains ones are the first, second, and third. Fourth one is an additional condition. So let's see which of these have been given to us. They have told us that it is small, it is spherical, and it is moving upwards. So it's the best thing to write the third point. You can also write the fourth point for safety, but when it's like for 1 marks, just write the main ones like first, second, and third. So you can just write the flow should be laminar, and you can also add another point for safety, that and it should have relatively low velocity. Okay, simple as that. So let's go to the next part. Okay, so we have this next part here. It says the bubble moves upwards at a constant velocity. The volume of the bubble is 5.3 times 10 raised to power minus 11 meter cube. Show that the upthrust on the bubble is about 5 times 10 raised to power minus 7 newtons, and the density of water is 998 kg meter per meter cube. Okay, so our first step, let's do it step by step. Our first step is to identify what values we have been given. So we have volume, we have we have density, and we need to find the upthrust. Okay, so what is the formula of upthrust? Upthrust is equal to the weight of the displaced liquid fluid. Okay, and the formula will be mg. Upthrust is equals to mg, but this mass is basically the mass of the displaced liquid. Okay, now we will use the densities formula, which is density is equals to mass by volume, and make it mass equals to dv, and then you are left with, instead of d, just use the symbol which is something like p. So use this density symbol v and g. Now if you input the values, we have density as 998 times, you have you have volume, which is 5.3 times 10 to the power minus 11, and you have gravity, which is 9.81, and if you multiply this, your answer will be 5.19 times 10 to the power minus 7 rounded off, and you will get 5.2 times 10 to the power minus 7. Hence we have proved our answer. Okay, so we have this next part right here. It says the bubble moves upwards at a constant velocity of 0.035 meter per second. Deduce whether the Stokes law applies to the bubble. You may ignore the weight of the bubble. Viscosity of the water is 9.5 times 10 to the power minus 4 Pascal second. So I have written some values from the previous part, which was, one is upthrust and the other one is volume. Okay. And I have to discuss one more thing with you guys, which is the constant velocity. Constant velocity means net force, right? Net force equals to 0, right? In other words, constant velocity is that it reached the terminal velocity. Okay. Now let's draw this. Basically, the thing I have just said, net force is equals to 0. So how will it look like in a drawing? Okay. So we have this bubble here, and if we had weight would have been acting downwards, but they ask us to ignore it. So now we have upthrust at upside, right? And it is moving up, so the drag force will be opposite to the direction of motion where it's moving, right? So if it's moving upwards, drag force will be opposite to it. So drag force is downwards. Now net force equals to 0 means that your upthrust is equal to drag force, right? So if it is equal to drag force, we are going to check it using our calculation. If they are equal, then it means that the Stokes law is applied here. Otherwise, it is not being applied here. So let's calculate the drag force. So we have drag force formula, which is 6 is equals to, sorry, not 6, my bad. It's F is equals to 6 pi r viscosity and V. So we have viscosity value and we have constant velocity, or in other words terminal velocity value 0.035. We don't have radius, so to get radius we can use our volume formula, volume of sphere, because the bubble is a small spherical stuff. So volume of sphere, right, is equals to 4 by 3 by r cube. We have volume, which is 5.3 times 10 to the power minus 11, and then you have everything value and you need to find the radius. Okay, so 4 by 3 pi radius r cube. Okay, now if you just shift 4 by 3 and pi over there, it will look like this, which is 5.3 times 10 to the power minus 11 times 3 by 4 pi, and if you shift this cube to the other side, it will be cube root, and if you solve it, right, cube root of all of this value, you will get your answer as 2.33 times 10 to the power minus 4 meter. Okay, so now you will use this radius here in the drag force formula. So F is equals to 6 pi, your radius is 2.33 times 10 to the power minus 4. Okay, and your viscosity is 9.5 times 10 raised to power minus 4 Pascal seconds, and you have constant velocity or terminal velocity as 0.035 meter per second. If you calculate the force value, you will get as 1.46 times 10 raised to power minus 7 newtons, right? Now, if we compare this value with the upthrust value, you can see that they're not actually equal. They're like far, far away, right? So you can just simply say that 1.46 times 10 raised to power minus 7 Newton is not equal to sine, and just say 5.3 times 10 raised to power minus 11. So it doesn't follow, or the Stokes law doesn't apply, right? Doesn't follow the Stokes law. Okay. So yeah, this is your final answer. Okay, so we have this next question right here. It says the photograph shows a floating object called a buoy. A long chain attaches the buoy to a very large mass at the bottom of the sea so that the buoy remains stationary. The water flow past the buoy causes a horizontal force 260 Newton on the buoy. The chain exerts a force F on the buoy at an angle of 33 degree to the vertical as shown. Okay. Show that the F is about 500 newtons. So it's very simple. First step is to draw your vector diagram, right? So here is our resultant line, which is your F line. This is your resultant line. And in order to draw a vector diagram, right, we have to reach here. Okay, remember that we have to reach at this red point. So you can only use up, down, left, right. So first you will go down and then you will go left side. Okay, so this is causing a 90-degree angle. Overall, it's a right angle triangle, and this is your angle 33 degree here. Opposite to this angle is always sine theta, and the line which is not a resultant line or a sine theta line, it is a cos theta line. Okay. Sorry. And then theta line. Okay, so now this is your first step done. Now your second step is analyze what values you can work with to get this F, right? So I can see that I can't use my vertical component, right? Because it is not actually, there's no other value except cos theta. So we can't use the vertical components, but we can use the horizontal components. If you can see that your left side, right, your left arrow contains F sine theta and your right arrow contains 260 newtons, right? This right here and this right here. So we can use this at our advantage and get the value of F. So F sine theta will be equal to 260 Newton. Okay. You can also write it F sine theta minus 260 Newton, but then you have to figure out what direction of motion you want to take. Like for example, if you want to take right side as positive, then your F sine theta will be negative and your 260 will be positive. If you want to take left side as positive, so you will have this thing right here which is like F sine theta as positive, and you have negative 260, which is now equal to 0 as well. You can write it this as this, like this as well, but it is completely up to you. I prefer this way because then I have to not select the direction of motion. So now F sine theta is 33-degree angle and you have 260 newtons. Now if you shift the sine theta downwards, right, because it's multiplying with F, so it will divide on the right side, so it's 260 by sine 33, and your answer will be 477 newtons. If you round it off to two significant figures, it will be 480 newtons, right? Why two significant figures? Because I can see that there are like two values, and even this value is in two significant figures. So just write your answer in two significant figures as well. Okay, so we have this next part right here. It says the buoy floats due to the upthrust from the water. The weight of the water displaced by the buoy is 2.9 K newtons. K is times 10 to the power 3 newtons. Determine the weight of the boy. Okay, so it's a very simple question. We will use the diagram. I will explain you through diagram. So this is our boy, and you have weight acting downwards and of course upthrust acting upwards, and you have one more force which is acting diagonally, like type of diagonally at 33-degree angle, which is this one. I have drawn the vector diagram here from the previous part, and this is your F force, right, which we found from the previous part, which was 477 Newton, right? Now you can see from the components as well that you have upthrust acting upwards and you have force and weight acting downwards, right? So force has a component cos, so we have F cos theta plus the weight, right? You can't directly use F, you have to use one of its components, right? So F cos theta is acting downwards. Now if you solve this, you will get the weight of the boy, right? So you have u, which is here, which is 2.9 times 10 to the power 3 is equals to f is 477, cos you have theta as 33-degree, plus you need to find weight. Okay, so if you subtract these values, you will get your final answer as 2500 newtons. Okay, so we have this next part here. It says the speed of the water flowing past the buoy increases, so the horizontal force increases. Assume that the weight of the water displaced by the buoy doesn't change. Explain how F and theta change when the horizontal force increases. So it's simple, right? First, make sure you have drawn your vector diagram, right? So this is your resultant line, and then you go down and left 90-degree, and this is your theta here. Okay, now what happened is that your horizontal force is increasing, right? So in order to balance it, or in order to make it stationary, it was mentioned in the part A that the buoy is stationary, right? In order to, right, keep the status of stationary, the F sine theta, which was here, and F cos theta, right? F sine theta here has to be increasing as well at the same time, right? So we have to just simply write this over here. But remember that F cos theta doesn't change, it because they assume that the weight of the water displaced by the buoy doesn't change. It means that the vertical component has not been affected at all right now. Okay, so now first we will write about our horizontal component, right? So horizontal component of the force, basically F, increases to maintain the status of equilibrium. Okay, and how will it maintain it? We have to explain it using the formula. So we can explain using Pythagoras theorem, which is a square plus b square is equal to c square. I know you might have heard about it. So let me draw the diagram. So this is your resultant force F here, down and left 90-degree, and theta here. So this is your FH horizontal component, and this is our FV vertical component, right? So you will write F square, right? This is your C. You can consider A or B this, or B A this. You can change A B, but don't change C. C is always the opposite to hypotenuse. This is your hypotenuse, opposite to this. So F square, equals to FV square plus FH square. Okay, so if FH is increasing, so if FH increases, then the F value increases, right? So we have to just say that. And the second thing we have to say that we can also, there's a second way as well, we can also explain it through the theta matter, right? Sine cos theta, right? So in order to explain it through sine cos theta, let me draw it again, the diagram. So you have F here, this right angle theta, and you can use the same thing again, FH, FV, vertical horizontal component. Now you can use the tan theta formula, which is opposite over hypotenuse, sorry, opposite over base. Tan theta is opposite over base, so opposite is FH by FV. So if your FV is increasing, sorry, not your FV, so your FH is increasing, then your angle will also increase, even if you just shift this tan to the right side, which will make it theta is equals to tan inverse of FH by FV, right? So even if your FH is increasing in this position, your theta will always increase, right? So you can just write the same formula here instead of this. Either ways, both will be correct. And if you decide to write one of them, then just explain that your F basically yeah, so F cos theta, because I haven't mentioned about our vertical component, so I can just say F cos theta, or the vertical component is constant, right? I forgot to mention that. You need to mention that as well. F cos theta is constant. So increase, right? I have mentioned that. Now you can see that. So increase in either the F or the theta value. Either ways, if you increase one of them, the other person will follow it. Like if you increase F, theta will follow it. Okay, implies an increase, right? In let me write in another line in the other. Okay, so we have this question right here. It says the student inflates a balloon. She uses a peg to keep the balloon closed. She then attaches a straw to the balloon using sticky tape. She passes a string through the straw and pulls the string tight as shown. The student removes the peg. Air leaves. The velocity of the balloon increases from 0 to max. Explain how Newton's third law of motion applied to the motion of the balloon during this time. Okay, so it's very simple question. So what is the first step? The first step that I always say is think simple, write simple. Okay, think simple, write simple. Okay, so then the mark scheme, or basically the examiner, if you can see that they never write too complicated stuff, right? They ask you for simple explanation, you give them simple and logical explanation in a structured way. Okay, that's the three steps you have to follow: simple, structured way, and it should explain the situation properly. Okay, now when the first step out of the way, so the second step is to understand what is actually happening when you remove the peg. Okay, when you have removed the peg, what happens? The balloon will release gas. Okay, so you have this balloon, right? It has a forward and a backwards direction. Okay, so when the peg is removed, the balloon will release its gas, and then when it releases gas, it provides a force to the air molecules, right? Or you can just say air. And you know the Newton's third law, okay, which is every action has equal and opposite reaction. Okay, so if we follow the statement, that means that if the peg is removed, balloon releases its gas and provides a force to the air in return will provide the force back to the balloon, right? So this is what actually Newton's third law says, right? Air will in return provide an opposite force, in other words forward force, to the balloon. So we just have to mention the first two things. Let's write it down so that we don't forget it. So what happens when the peg is removed? Okay, the balloon releases gas, and then it actually the balloon releases gas and it provides the force to the air. And we also have to mention, like, it's better to mention the direction where the force is being provided. So he is providing the force backwards. He, in a sense, balloon, okay, backward force, backward force. Okay, so due to Newton's third law, air in return will provide the balloon an opposite balloon and opposite force, okay, which is our forward force. So we have mentioned these two things. Now let's go to the next step. Okay, what is the next step? Next step is when all of this when all of these things happen, it receives the forward force and it starts moving, right? From this point, the velocity of the balloon increases from 0 to maximum, right? So we have to explain the statement: velocity from 0 to max. What is happening between this thing? Okay, so it receives the forward force. Now you're just okay. I have to explain one more thing, that you're not just bounded to explain this question to only with Newton's third law. You can explain it with anything else, right? It did not say that only explain me Newton with Newton's third law, right? It's not possible, because if you want to write 6 marks, right, Newton's third law doesn't say that much, so you can write 6 marks. You need to have other things included so that you can get this whole 6 marks. Okay, so let's get back to our step. So velocity goes from 0 to max. So when it receives the forward force, acceleration will increase as well, right? And how? Due to Newton's second law. Okay, which basically says that your net force is equal to the mass times the mass is the product of mass times acceleration. Okay, so if your net force, which is actually your forward force, is increasing, so your acceleration will increase as well, right? It will cause acceleration. So now the velocity, or you can say speed, goes from 0 to max. So while it's going from 0 to max, okay, the force will change. Okay, so it won't be like you have a fixed force. It's like you're increasing slowly, right? And when the balloon is like actually going forward, you can just say that when it's going actually forward, the forces, uh, the best way to explain is that the resistive forces, there will be a time when the resistive forces will be equal to the forward forces. Okay, how so? Because number one, they never mention that air resistance is negligible. So you have to mention about the air resistance or the resistive forces. So when the balloon is going forward, it will have challenges with the resistive forces, right? Not at the start, but later on when it reaches to the max velocity, right? And what do we mean by max velocity? It means that our net force is becoming zero, which means that our forward force is being equal to the resistive force. Now you won't see balloon going forever and ever, just flying everywhere. There will be a time when the balloon will come down as well, right? So it goes to this thing where the net force becomes zero, and when that happens, the speed doesn't increase anymore. Okay, by the Newton's third law, the speed never increases anymore. And Newton's third law is not that complicated. It's a very simple thing. It's about inertia. If the object is at stationary or it's at zero, it will stay at zero. If it's moving, it will constantly move unless there is any external force. In this case, we have resistive external force, so it later on will come down. But we only have to explain through 0 to max and not max to 0. So just explain to 0 to max about all of this thing. So I'm gonna write it out so that you understand the step by step what I'm doing. Okay. So the after we receive this forward force, it will be greater than resistive force. That's why it will be going forward. Okay. So the forward force is greater than the resistive force, right? So due to Newton's second law, the resultant force will cause acceleration. The resultant force causes acceleration. Okay. Now we go from 0 to max, right? So the speed is increasing, right? As speed is increasing, right? The force is still changing, means the balloon will still receive challenges against resistive force, right? The force is still changing until it reaches to a point, until it reaches to a point where the resistive force will be equal to forward force, right? And this is what Newton's first law comes, right? Newton's. Now you can just write semicolon and say Newton's first law comes into action where if the net force is zero, then the balloon will not accelerate anymore. Okay, so it will be actually be equal to, in a sense, zero. Okay, at max speed. Okay, so this is all of the stuff you have to actually explain. You have to first explain the point when the student removes the pegs and air leaves the balloon, or gas leaves the balloon. And the second thing you have to explain is the velocity of the balloon increases from 0 to max, right? So he mentions two statements. Now think of the examiner as he's super dumb. So you have to explain these two statements that he asked from you, right? In the form of Newton's laws, right? You're not only restricted to Newton's third law, you can explain it through all of the laws, right? And all of the stuff. If it said only, then you are restricted to only one stuff, but you're not restricted in this case to only one stuff, right? And you can't actually explain everything only using Newton's third law, okay? All of the process. It requires you to explain from Newton's second law and first law, okay? So yeah, this is your final answer. Okay, so we have this next question right here. It says the diagram shows a crane lifting a load. There's a large mass called counterweight attached to the crane on the opposite side of the tower. The crane has a electric motor with an efficiency of 47%. The crane lifts a load of 4.4 times 10 raised to power 4 Newton. The load moves through a vertical distance of 15 meters in a time 70 seconds. Determine the average power input of the electric motor. Okay, so one thing I want to mention is that this thing, counterweight, is just a distraction. So just avoid this. Understand what values you are given, right? So first step, understand what values are given, right? Note down what values are given. Understand the values given. Okay, so I have force, I have the height, okay, because it's lifting load from here to here, 15 meters, right? Height is 15 meters. So you have force, you have height, you have time, and you have efficiency's value, which is 47%, okay? And it's the efficiency value. So now you need to find average power input. Just remove average so you're left with power input, right? So if you use the efficiency's formula, right? Efficiency is equals to useful power, right? Over input power, or you can say the total power, okay? So efficiency given, you need to find useful power. How we will find useful power? You can see that this box was lifted 15 meters above the ground in 17 seconds, right? So we can use power formula, right? Power is equals to W by T, right? To get this power, right? To get this input, sorry, not input, my bad, useful power, okay? So to get this useful power, you need this work done. Work done, in other words, is also energy. So there are actually two ways I can see that. You can use one of this formula, F into displacement, change in displacement. But like honestly, like the way I understand it, just make it simple, right? So if you can see there's a change in height, instead of what, you can use this and you will still get the same answer, okay? But what I prefer is that understand simply, right? So you're moving from the box from ground to above level with the height. Whenever an height is mentioned, I always think of energy, and energy's formula of gravitational potentials energy, right? Gravitational potential energy, which is mgh, right? So you can use this formula. I recommend you can use both, right? But I recommend thinking simple, and whatever comes in your mind first, use that, okay? So this thing came in my mind first, so I'm going to use this. So for mass part and for gravity part, let's see. So mass and gravity can be written as W and H, right? Weight and that stuff. So you have been given that this weight is 4.4 times 10 raised to power 4, right? And then you have the height, which is 15 meters, okay? So if you calculate this value, you will get 6.6 times 10 raised to power 5 joules, okay? Now you can use this joules in power's formula, right? So, okay, let me write it down here as well, so it's much more neat. So, gravitational potential energy, let me write it like this. Gravitational potential energy is equals to mgh. You can also write it as wh, because w is equals to mg, right? And you have weight, you have basically the weight of it. So it's 4.4 times 10 raised to power 4. Height is 15, and the rounded off value I got was 6.6 times 10 raised to 5 joules. Don't use rounded off values. Better to use the value you have been given. I don't have a calculator right now with me, so I've already written the value for it, right, in a rounded off version. So now the next part is that what you need to do is you need to use power is equals to energy by time or work done by time. If you get your answer from work done, use work done. I got my answer from energy, so I will reuse my energy symbol here. So it's 6.6 times 10 raised to power 5, and time is 70 seconds. So now if you solve this, you will get 9.4 times 10 raised to power 3 watt. Now you can use this watt because this is the useful watt. So you can use efficiency equals to useful over total. So efficiency is 47. In other words, it will be 0.47. You don't write in percentage, you actually write in numbers, basically in decimal. And useful is what is useful? Useful is 9.4 times 10 raised to power 3. And then you need to find total. Now if you calculate the value for total, you will get as 2 times 10 raised to power 4 watt, okay? 2 times 10 raised to power 4 watt. Okay, so we have this next part here. The horizontal distance from the load to the tower can be changed. The horizontal distance from the counterweight to the tower can also be changed. Explain how the counterweight needs to move when the load is moved away from the tower. Very simple, dude. Like, honestly, I'm going to explain in a very simple way. First step, okay? Identify what could go wrong. If I basically increase the right side and I don't increase, basically I change the right side and I don't change the left side, if the clockwise moment is not equal to the anti-clockwise moment, then what will happen? The tower will break and it will basically fall down, and we don't want that. So first thing we want is total clockwise moment is equal to total anti-clockwise moment. Okay. Second thing, identify what is clockwise and what is anti-clockwise. Some people do make mistakes when they do not identify what is clockwise and what is anti-clockwise, and then once they figure out later on that they have chosen the wrong clockwise and anti-clockwise, they have to do the whole question again, and you don't have time in exam to do the whole question again. Okay, so further identify this, which is clockwise and which is anti-clockwise, right? Clockwise and anti-clockwise, what are those? So this is clockwise, right? Clockwise, this means basically if you see a time, it goes, it moves on the right side and move clockwisely. Okay, and anti-clockwise is like basically the opposite, moving the opposite direction of the clock. Okay, the seconds arrow. Okay, I'm talking about the seconds arrow. So this is clockwise and this is anti-clockwise, right? So you mentioned that our load is clockwise and our counterweight is anti-clockwise. Now third step, what is third step? So let's say for now this is 22 because it says 30, right? 30 meters, so 22. If I increase its distance, right? Let's say I make it 24, what will happen? So as you know that we have the formula F into D, right? Clockwise and anti-clockwise. Moments formula is F into D, right? And the same thing, clockwise and anti-clockwise have the same thing, F into D. So if I increase the D, basically I increase it to make it 24, then of course I cannot change force. I cannot change the counterweight's force, right? It's already up in the air. It won't automatically increase its force, right? It won't increase it. So you have to increase its distance as well. So if you're increasing the distance for the load, if you're making it further away from the tower, then you have to also make counterweight further away from tower, right? It doesn't make sense. Yeah, so we just simply have to write this whole thing and that's it, nothing else. Okay, so first step, let's write the total clockwise moment is equal to the total anti-clockwise moment. And then the second thing you say that if it's not, if it is not, then the tower breaks. You can just say breaks. Okay, so we have mentioned that. Now you can say either way which is clockwise and which is anti-clockwise. Just identify them. The load equals clockwise and the counterweight, wait, counterweight is anti-clockwise. Okay, anti-clockwise, you have mentioned that. Now the third step is if I increase the distance between the tower and the load, the what value will increase? The clockwise value will increase. In order to make clockwise and anti-clockwise equal, we in order to make so we need to increase distance between the counterweight and the tower, right? And then increase the weight and basically increase the counterweight, increase the distance between the counterweight and the tower so that it remains balanced. Okay, remains balanced. So simple question, and you just write the simple logical answer, right? Don't write anything complicated. It is not required here. Simple thinking, simple answer, and yeah, just portray your simple answer here, and that's your final answer. Okay, so we have this next part right here. It's a very interesting part. We have that the beam is uniform with weight this, counterweight has a weight this, load has a weight this. Deduce whether the load can be moved at the end of the beam without the crane toppling. So it's very simple, but you have to follow some steps, okay? So the first step, identify what values you have been given, okay? I always say that. Identify what values you have been given. So you have three weights: uniform beam, the beam's weight, the counterweight, and the load weight. Okay, and then you have two distances, right? We have the distance from center to counterweight and the whole, basically, is the length of the uniform beam. Now you have identified that. You remember that you have moment. You're taking moment at center, right? This is the center, right? Basically the pole. Okay, so we will do all of our calculation according to this statement. Okay, so 8 meters is from center to counterweight, right? Now second thing, important step here, read the statement again and identify if there is any hidden meaning, not normally not hidden meaning, but like anything useful that we can use for to solve this question. So you can say that, you can see that basically it said uniform, right? That's why I also highlighted uniform. Uniform means that the weight is acting at center. Okay, so center is somewhere here, because if you divide 30 by 2, it's 15 meters, right? So 15 meters come from here, whether you go from left to right or right from left. Okay, now you have to identify again what moment at center, right? We are taking moment at center, so we have to decide the how much distance it is from center to the weight of the beam. Okay, so it's easier to do it from left to right. Okay, so let's do it. Sorry, meters. Okay, so now we do 15 minus 8. Okay, so you will get 7 meters, right? So you subtract this from here, like from 15, this total 15, you subtract 8, and then you will get this much, which is 7. So this is your weight of beam. Okay, simple as that. Now that is out of the way. Now the second thing is, you need to understand that clockwise moment is equals to anti-clockwise moment, right? If it doesn't follow the rule, it will anyway will topple, the crane will topple without even moving the load. Okay, so it needs to follow that. Now we don't know what's the how much limit do we have, like from the center of the pole till the load, how much we can move, right? So we're gonna keep this thing as x, right? So we can see how much max can we move, right? So we're gonna use this formula, and moment has a formula of F into D. So counterweight is, remember that you need to also identify that yeah, I didn't write this, so identify anything useful in question. And the third thing is identify what was I about to say, I forgot. Identify the clockwise and anti-clockwise moment, right? So this thing I wanted to say, identify your clockwise and anti-clockwise moment. Okay, so this is your anti-clockwise. Okay, and these two things are your clockwise. Okay, so write them properly. Okay, so clockwise is what? So I have clockwise as 3.0 times 10 raised to power 4. So first we will do the beam times the distance, which is 7, and then you have plus the load, which is 4.4 times raised to power 4, and then we don't know, it's x, right? How much we can go further before, if we move it further than that, it will topple anyways. Without, remember that we're not doing the previous part again. Previous part they said we can change the distance. In this part they did not say we can change the distance of the counterweight, so remove that thought from your mind. Okay, we cannot change any distance for the counterweight, right? We are just only seeing that how much further can we move the load before it topples, right? Can we move it till the end of the beam without changing the distance from the counterweight, right? Center to counterweight. So you make it equals to the anti-clockwise, which is 1.1 times 10 raised to power 5 times the distance, which is 8, okay, from the center. And now if you solve this, like completely solve this, right? If you let me arrange it properly, and then we will write the answer. So it goes 1.1 times 10 raised to power 5 times 8 minus 3 times 10 raised to power 4 times 7 divided by 4.4 times 10 raised to power, sorry, wait, it's wait, how much is it? It's 4.4 times 10 raised to power 4. Yeah, that's it. Okay, so now we have done this much. 4.4, it's, sorry for my bad writing, it's 4.4 times 10 raised to power 4. And then if you solve this, you will get a distance of about 15.2 meters. Okay, I have the rounded off value with me, so 15.2 meters. And you can see that from here to here, let me use red color a bit so that it's much more visible. So this much is 22, right? After you minus 8, right? So till the end, it means that you have to move it till 22 meters, but you can't actually move it because at this point it reaches its max equilibrium, right? Max equilibrium point, how much max you can move the load. If you move further than that, it will topple without any reasons, right? You can't, remember, you can't move the counterweight, right? If it exceeds 15.2 meters, it will topple without any doubt. Okay, you simply just write that 15.2 is less than 22 meters. So if we move it, if we move it means load, if we move load at the edge, the crane, it's crane, right? The crane will topple. Okay, yeah, the crane will topple. Okay, simple as that. Okay, so we have this question right here. It says an actor is wearing a harness. The harness is connected to a cable and support as shown. The force on the cable must not cause the material of the cable to reach its yield point. State what is meant by the yield point of the material. It's simple. It's a book definition. Yield point is something like, it is a point where if the force is increased, it will go under a sudden or a large deformation, plastic deformation. Okay, so it's a book definition, just simple, right? That the stress value, even you can write strain value, any of those value, when it reaches stress value at which a material undergoes a certain, sorry, a certain or large deformation. It's like nothing new, like it is nothing much to explain. Is that if you have seen a spring, right, if you just like stretch it out a lot, it will reach to a point where it won't go back to its original shape. It will be much more extended. That's basically yield point, right? Where the sudden basically deformation starts and it won't go back to its original shape or form. Okay, so we have this question right here. The cable and harness are used to accelerate the actor vertically off the ground. Explain why the forces acting on the actor cause him to accelerate upwards. It's like very simple thing. Like how can, and actor could go basically up, right? When basically this is your actor right here, okay? So this is the actor's weight and this is the cable him provided, right? If the tension value, if the upwards force value, in other words, the tension value is greater than the weight value, then if he will go up, the resultant force will be upwards, right? So it's simple as that. You need to explain that so that the force, in other words, is also called as tension, is in the cable. Make sure to mention that the force in the cable, you can't just simply say force, the force in the cable is greater than the weight of the actor, so the resultant force will be upwards. Okay, properly upwards. Okay, so yeah, this is your answer. Okay, so we have this next part right here. It says the actor has a mass of 77 kg and is lifted vertically from the ground with an acceleration of 2.1 meter per second square, and you need to find the tension of the cable. Okay, so it's a very simple question, but you need to do it step by step. Without steps, without strategy, you can't solve this question. Okay, first step, identify the values you have been given. Okay, so if you identify the values you have been given, so you have mass and acceleration, right? And you need to find the force, or basically, in other words, the tension, right? You need to find tension. So most of you, I know what you guys will do is that you will directly do F is equals to ma and then put mass and acceleration and blah blah blah, and we'll know that, oh well, it doesn't match. What is happening here? It is because you don't know the Newton's second law properly, because this formula is Newton's second law and you don't know that properly, right? So let me explain you Newton's second law properly. Okay, Newton's second law says that net force is the product of mass and acceleration. He did not say that force is the product of mass and acceleration. He said net force is the product of mass and acceleration. So how we will write it? We will write it like this. This is your net force, right? So we do have mass and we have acceleration. Do we have included all of the forces in the net force category? No, we did not include everything. We just said that this is only tension. We only have tension. Where's the weight? You forgot about the weight, right? So let me draw this. This is the actor. We have weight acting downwards and then we have tension acting upwards, right? So now you can take any motion of direction, positive, right? Up positive or down positive. I will take down as positive. So if you take down as positive, your tension will be negative. So it is written as W minus T. This is your net force and MA. So you don't have W. You can find W from multiplying mass with gravity. W is equals to mg. So if you do 77 times 9.81 minus tension equals to the 77 times 2.1. Okay. Now if you solve this whole values, you will get your answer as, I have the rounded off value with me, so it's 917 Newton. Okay. Okay, so we have this next part right here. It says to make sure the actor is safe, the stress in the cable must be less than 15% of the yield point stress. The cable has a yield point stress of this. The diameter of the cable is given. Tell me whether it's safe if we move the actor with this much acceleration. So first step, identify what values you have. Okay, what values you have. Okay, now I have basically, I have the limit, I have diameter, and I need to find the stress. So right off the bat, let's eliminate the first point here. So let's figure out the limit we have. So it's 15%, which is in other words 0.15 times 2.5 times 10 to the power 8 pascals. So if you solve this, you will get your answer as 3.75 times 10 raised to power 7 pascals. Okay, this is the limit. Okay, we can't exceed this limit, otherwise it's not safe for the actor to use the cable. So let's find the limit now. So stress, we need to find stress. Stress formula is F by A, right? And we do not have A, so we can use this formula to find A, which is pi r square. Why pi r square? Because our wire is having a circular shape, and this is area of circle, so that's why we use pi r square. So let's input the values. R, in order to find R, you can do it diameter divided by 2 because we have diameter. So 7.6 times 10 raised to power minus 3 divided by 2 and square, and then put this in area. Here you have force from the previous part, which is 917. Area is 7 pi times 7. Wait, let me go a bit more down. 7.6 times 10 raised to power minus 3 divided by 2 square. Now if you solve this, you will get your answer as 2.02 times 10 raised to power 7 pascals. Okay, so now you can see that this value is less than this value, so it's safe for the actor to move across with this much acceleration. Or how much acceleration was it? 2.1 acceleration. Okay, you just simply say that 2.02 times 10 to the power 7 pascals is less than 3.75 times 10 to the power 7 pascals. So it is safe. Simple as that, right? Faster, right? Okay, so we have this next and last part right here. It says the original cable is replaced with new cable made from different wire, right? Highlight all the important points. Cable is replaced with new cable, different material. This material has lower Young modulus than the material used to make the original cable. Okay. The new cable has same length as the original cable but has a greater diameter. The breaking stress is same for both cable. Explain how the work done to break this new cable is different from the work done to break the original cable. Assuming both material obey the Hooke's law up to the breaking point. It's very simple. Okay, let's do it step by step. Okay, so let's first write the formula to understand it, right? So first step, write formula. So what is the formula? The formula is Young modulus equals to stress by strain. Okay, so we're just talking about the new material, right? This just the only new material. So he says that basically they say that the Young modulus is less, right? So now the Young modulus is less. Now the first thing that comes in my mind, right, without reading any further, just the Young modulus is less, is that either the stress has to be same and strain has to be greater, or stress has to be less or strain has to be greater, or just the stress has to be less and strain doesn't change at all. Okay, this way the Young modulus will stay less at all times. Okay, so this statement come in my mind, right? This thing just instantly come in my mind. Okay, second step, now this said that the stress is same. Okay, the breaking stress is same, so we eliminate this point here, this point here, this point here, this point here, means that the strain is greater, and we reach to a conclusion that strain is in this case is greater and stress is same, right? In that case only the Young modulus can be less. Okay, simple, right? Now we have to explain it. We can't just say, oh well, because of the formula, because we have to mention this in 4 marks, right? How we will mention it properly. So let's dive into the stress and strains formula, right? Now stress is F by A. So they said that the diameter is greater, right? And the, let's say, did they say anything else? Diameter is greater, breaking stress is same. Okay. So if diameter is greater and they want to keep the stress same for both cables, that means the force has to be greater in order to match, in order for this stress to be matched up. Okay, because if you only increase area, then the stress will be less. If you only increase force, then the stress will be greater, right? Just I'm explaining that you have to make both values to be equal, otherwise the stress will have a varying values. It will be not same as the other cable, the old cable, the original cable. Okay, so we have came to a conclusion that if the diameter is greater, area is greater, then force is greater. Okay, force needs to be greater. It's required that we need a greater force to make it, sorry, to make the stress not be changed. Okay, now third step, let's go for strain. Okay, so how this strain value is greater? So it says that it has the same length, right? We know the formula of strain, which is extension by original length. So original length is same, but if original length is same and the strain value is greater, then the extension has to be greater. Okay, simple as that, right? If strain is greater, extension has to be greater. If the length of the cable is same. Okay, for both of the cables length are same. Okay, original and the new one. Okay, so from these I got to know that the if the a diameter is greater, area is greater, then the force is greater. If force is greater, then and for the strain part, if the original length is same, then the extension has to be greater. Okay, simple. Now if these both things are greater, do you remember the formula of elastic strain energy, right? Basically, you know that work done is energy. Okay, so elastic strain energy has a formula of 1 by 2 F delta X. Now they are both increasing. So energy increase, work done increase, means you need more work done to break this new cable, right? That's how it is different from the original cable. Okay, so we have to explain all of this in a very simple way. Okay, so first thing we will mention is that about the stress thing. Okay, what about the stress thing? That the new cable has a greater basically cross-sectional area. We always say them cross-sectional area, not only area, cross-sectional area. So if it has a greater cross-sectional area, then it means the force is required to be greater. Is required to be greater. Okay, first thing out of the way. Okay, and we also have to give the reason. We only just stated something, but we didn't give the reason. What is the reason? How I can say that this point that I have mentioned is valid? Because I need to give the reasoning as well. Because new cable has low Young modulus, and there will be greater, oh yeah, this is, sorry, next point, there will be greater strain, right? Why? Because the Young modulus is low, right? So as we have discussed the third point, there will be greater strain. And how so? How the strain will be greater? We have to mention that the the length is same for both cable, so the extension has to be greater in order for strain to be greater. Okay, now we have given our three statements here. Now the final thing, like what effect does it have in the work done? We can say or use the formula that we can also mention the formula, or if you don't want to mention the formula, just write the statement, right? So just say E is equals to, not E just like work done because they specifically ask work done. So work done is equals to, they're both the same, okay? Don't worry, they're both the same. Don't freak out. So 1 by 2 F delta X, right? This formula. If both F and delta X is greater, then the work done will be greater in order to break this new wire, right? We need a lot of work done to break this new wire than the original wire. That's the only difference.